Okay, as I said at the very beginning, we're starting set 7 of our lecture notes, which is available in the Piazza. And this week's topic is sensitivity analysis. All right, now we all studied the optimization problems, believing that, or under the certainty assumption, all right? We all the parameters will always be the same, and then we optimize based on the parameters. Now, what happens if, like, you're selling the price for $10, and all of a sudden, the marketing department tells you that the price will be 11? Would you have to solve the problem from scratch? Or can you utilize the solution that you already have, which is valid for $10, and move from there to the solution for $11? Okay? This is called sensitivity analysis. So how sensitive is your solution on your hand to your problem parameters? How far can you change the profit margin or whatever the increment there and remain optimal with your current set of decisions? This is the underlying question or the research question under the sensitivity analysis topic. We will start with discussing a little bit more on duality before going to the theory of sensitivity analysis, because there's actually, even though I know I defined you the duality by saying that, it's a definition. If there is, for any LP, there exists another LP that's called the dual. Yeah, mathematically, everything is valid, strong, and sound. But if you want to make a meaning out of those dual variables, well, we can actually. That's what I'm going to do right now. So be careful. We have already defined those from a mathematical point of view. But now I'll actually give you a way of looking at them where they may have some meaning, actually, in economic meaning. So let's look into this problem, okay? We have our good old canonical for max-min primal dual pair. Okay. Now, we know from all those duality theorems, right? We have the weak duality theorem, strong duality theorem, complementary slackness. So we know that there are very nice relationships, mathematical relationships between these two pairs, between a primal dual pair. Now, let's focus on from the primal's perspective. Okay. Let us get the optimal basis from the primal. We know that the dual will be CBB inverse, right? We have seen this. Okay. Now, let's see. Now, for the basis being B, my optimal objective function value is CBB inverse B, right? That's what's written on the simplex table when we continue our iterations. And if you want to remember, let me put here this simplex table for any B. For any B, my simplex table looks like this. Here I have XB. Here I have B inverse A. Here I have minus C plus CB B inverse A. Here's B inverse B. And here's CB B inverse B. Right? Depending on how you write your columns, your XBs, XN, or if you carry your starting BFS, whatever, this table will get identity somewhere and zeros under those basic variables. Okay, but the general format is actually this. If the column of the A is coming from identity, it goes B inverse B, which is 1 or 0, right? So anyway, this is how the table looks like. So as you see from here, this is my objective function, CBB inverse B. Okay, now let's look at the ith entry of that dual vector, CBB inverse. Yeah, because dual's variables are in dimension M because they're for each constraint. And let's look at the ith entry of that dual vector, dual variable. Now, well, it looks like if I were to take the derivative of my objective function with respect to my right-hand side, I would get the ith entry of CBB inverse, right? Which is my ith dual variable. So it's actually resembles like the rate of change, right, of the optimal objective function value, because I'm taking the derivative of my objective function value with respect to a unit increase in the right-hand side of the ith constraint, because ith constraint is associated with the ith variable, okay? All right, now let's consider our primal problem, meaning maximizing Cx subject to Ax less than or equal to P. Now, let's give meaning for our variables, right? So let's say that we have resources from B1 to Bm, and we're going to utilize those resources, right? Is this actually, yeah, let me get rid of the chat because I think it's on top of, okay. Now, I have M resources, and I'm going to produce N products using those resources. Each product comes with a profit, right? And each product consumes some of my resources. So Aij is my consumption parameter from resource I of the product that I'm produce J. So I have N different products. Then actually this is my resource constraint, right? Each resource I cannot be used more than what I have. And this is my canonical form max problem with the meaning that we just attached to it. So I'm maximizing my profit of the products that I'm producing. Each product consumes some of my resource, and I have to obey my resource limitations for all my resource. For all I, this goes from 1 to n, and j goes from 1 to n. Okay? That's how it is. Okay, now here, that's my problem. I want to find out the best combination of those products so that I'm using those resources and I'm maximizing my profit. Okay, that's me, my canonical form max problem. Now let's look from the dual's perspective. Okay, there is another entrepreneur in the market. That guy wants to buy my resources. Remember those B1, B2, Bm? I'm using them to produce my products. So there's another entrepreneur in the market, and he wants to buy those B1 up to Bm. All right, that's a different way of business. Maybe we may allow that. But then the entrepreneur must to find out how much he or she should pay for my resources. So for each resource he's going to determine a price. Okay? Those prices, because it's from 1 to m, let's name them as WIs, which are actually our dual variables, by the way. So there's an entrepreneur in my market again, where I'm playing to maximize my profit. There's another guy who wants to buy those resources and putting prices there. Okay? Now, this game should be fair, right? So the entrepreneur must give me fair prices so that instead of producing my products, I may think about selling my resources, right? So, well, this is what I get for each product J. Yeah, that's the profit. Now, and the product J is using Aij from ith resource. So for each resource that he's buying with the price, if this summation here is actually, if this summation here, Aij is larger than my profit for the product J, so for the consumption of the product J from that resource, multiply with the resource per unit price I'm going to get from the entrepreneur, I may think about selling my resource rather than producing it, right? That brings me to entrepreneur's problem then. Entrepreneur wants to buy the resources with minimum total cost because for him it's the cost. So he wants to minimize the prices times the amount that he's buying. but he wants to make sure that the problem is fair. I may think about selling my thingies. And what is this? This is my canonical form min. So from this perspective, okay, the problem goes from, so for a primal canonical form max, I actually ended up with a canonical form min dual problem. We defined it for the mathematical representation, and now, well, we actually managed to bring some economical meaning to it. Now, okay, let's remember those theorems we derived and proved last week. The last theorem we discussed was complementary slackness, and complementary slackness was saying that if the constraint is not binding, the multiplier should be 0. Now think about it. If I'm not using all my resources, then the entrepreneur could get them for free because I have leftovers, right? So it doesn't make sense for him to give prices for those guys. So if there is an excess amount of resource I, then the associated price for that resource should be 0 because I'm not using it anyway. From the other way around, from the dual's perspective, if what entrepreneur giving to me should be larger than what I'm going to get as my profit, I'm definitely not going to producing anything. So my XJ will definitely going to be 0, right? So this is the economic interpretation of the CS conditions also. Any questions? I have turned off the chat screen, so if you're writing anything to chat, I won't be able to see. Okay, nobody did anything to the chat. Then I'll go on. Okay. Now, I told you we're going to actually work on sensitivity. But before that, I have to teach you the dual simplex, because that's a different, it's again simplex, but in a different domain, because we're going to utilize this version too in the sensitivity analysis. So we're getting our Bayes ready. So dual simplex. Now remember the optimality conditions. Now you know this, right? Remember the normal simplex. That now becomes the normal simplex, because there's another simplex that works from the dual perspective. But the simplex that you guys know up until now is going to be called primal simplex from now on, because it works on the primal problem. What do we do in that simplex? We always have feasibility, right? Because that is, if it is not there, we solve a big gam or two-phase, whatever, so that we end up with a feasible problem. So it's always there. We have to have feasibility. Remember, I told you last week, every simplex table satisfies complementary slackness conditions. I even proved that last week, right? For non-basic variables, the variable itself is 0, so the multiplier doesn't matter. For basic variables, the row 0 coefficient is 0. And from primal's perspective, the problems for AX equal to B anyway. So in the simplex that you guys are always doing, all right, up until now, so complementary slackness conditions are always satisfied. Primal's feasibility, that's how we start simplex. So we need that one too. Now, what are we working towards? Is what we utilized in the proof of strong duality is dual feasibility. So the primal feasibility and complementary slackness is always with us in the simplex algorithm, and the algorithm stops when the dual becomes feasible. What is the dual? CBB, right? When is the dual feasible? Well, when my row 0, when my row 0 here becomes non-negative, because WA greater than or equal to C was what I asked, and here actually it was written, let me clean it and write it again. Sorry for the thingy. But what do I have? I have x b x n 0 minus cn. Let's write it like this time. cb. It's the same thing, by the way. I just partitioned with respect to basic variables and non-basic variables. So I'm going to have xb in here. Here I have b inverse b. Here I have cb, b inverse b. Just, this is exactly equivalent with this guy. Here I have xb again, but I don't know. I didn't shuffle the columns. So here I have minus c plus cb, b inverse a. Depending on the coefficient, it becomes, and here I write b inverse a. I don't know. I didn't shuffle. But this is b inverse b, by the way. Here we have b inverse b. And here we have cb, b inverse b. Now, why did I write this? Because I was going to actually point out that complementary, we stop when the dual is feasible. Dual feasibility was WA greater than or equal to C. This is when our row 0 is all non-negative for our maximization problem, right? So, interestingly, we proved it from other way around, saying that there is no improving neighborhood anyway. But then what actually we were doing was we were having feasible primal, which also satisfies complementary slackness with its dual partner, which is CBB inverse. And we stopped when the dual problem became feasible. This is our simplex, good old simplex. Now, today I'm going to teach you another simplex, which we call the dual simplex. Dual simplex, it's again on the simplex table. So complementary slackness conditions, again, is always maintained. So we always have a prime dual pair, the simplex table, that satisfies complementary slackness conditions. Fine. Now, this is dual simplex. So we move from the duals problem. So the dual feasibility is maintained. We stop when primal becomes feasible. All right? So optimality condition, primal feasible, dual feasible, CS conditions satisfy. All right? Primal simplex maintains primal feasibility and CS, moves towards dual feasibility, meaning row 0 non-negative. Dual simplex maintains dual feasibility and complementary slackness, stops when primal is feasible. What do I mean? So dual simplex starts when this row 0 is non-negative, but it's okay to have right-hand side negative. And dual simplex stops when the right-hand side becomes non-negative too. Okay? Any questions? Let me breathe so that you can ask questions. Any questions? Okay. Then, let me go on if you're not asking anything. Now let's drive the machinery for the dual simplex algorithm. Again, we're going to do it for max problem as we did in the primal simplex, okay? For the sake of dual, we're renaming our thingies. What do I mean? For everything in here, let me switch to a different color. Everything in here, okay, I'm going to use a name Yij, all right, for ith and jth entry. It's B inverse A, as you see, and it's B inverse A's ith and jth entry, okay, which is B inverse AJ's ith entry. So this guy here is going to be called Yij because I need that. I will use it in the ratio test again. What else do I have? Row 0 coefficient minus C plus CBB inverse A. Minus C plus CBB inverse A, but every X has a row 0 coefficient, so it has a jth entry, and that jth entry, we're going to name it as RJ, all right? This is my B inverse B. It's written for every constraint, so it has an entry again, so I'm going to name it as QI, which is B inverse B's ith entry, okay? Keep these in mind because we're going to utilize that in the dual simplex algorithm. What did I tell you? Dual simplex says the dual is feasible. Now, what is the rule for dual to be feasible? Row 0 non-negative. So when I start this algorithm, I will have all my RJs non-negative. All my row 0 will be non-negative. So from Primal's perspective, my simplex table would look like it's optimal. Okay? But then if this is also non-negative, that means, well, from RJ, dual is feasible. From RJ, this means dual is feasible. If all right-hand side is non-negative, that means primal is feasible. And I told you in a simplex table with CBB inverse, complementary slackness is always satisfied. So this table would really be optimal from every perspective, from primal's perspective, dual's perspective. Okay? This is the idea of the dual simplex then. We're going to start when these guys are non-negative. So from dual, the dual problem will always be feasible. And we would move towards primal feasibility. So the ratio test, remember in the simplex algorithm, ratio test was actually guaranteeing the feasibility of my next step, the primal feasibility of my next step. This time, my ratio test would guarantee that I would remain dual feasible. So I would remain non-negative in the row 0 at each step, at each iteration. Okay, here is the wordings of the algorithm. If right-hand side is non-negative for every I, that means primal is feasible, you can stop. Optimal. Otherwise, that means there is a guy in here with a negative right-hand side, with a negative value. There is a QI with strictly less than 0. Remember in the simplex, we were entering the most negative. This time, again, we're going to do the most negative, just for the hope that we would go to the optimal in a shorter amount of iterations, shorter number of iterations. So we pick the most negative QI, whatever that is. Now, that variable will be our living variable. It's already in the basis, but it has a negative coefficient there. I don't want that, right? So we determine the living variable first, and based on the living variable, we're going to determine the entering variable. I don't know why I can't go to my next empty page. I already have enough, but somehow, because I was going to write these, okay, that means I have to use the same board all the time. Hold on. I'll do my best. What I'm going to do is I'm going to write these things here so that we would... There is a problem, but yeah, it's not working. My screen is not working. I don't know why, but my screen is not working. Oh, there it is. Maybe it works in here. Anyway, I'll go from here then. Remember, we named, okay, then I'm not using that part. Remember, we named row 0 coefficients as R and the matrix coefficients as Yij. And right-hand side is Qi, okay? So when Qi is negative, that means I'm picking this guy, which is basic. And I want this guy to leave the basis because in the current situation, it has to get a negative value, which I don't want. So I'm determining my leaving variable first. Now, I will determine my entering variable. Well, the entering variable should maintain my row 0 non-negative, right? So the ratio test would go from these guys. So I have to make sure that once I do those matrix iterations, the elementary row and column operations, because this guy is leaving, so I'm going to determine an entering variable, and the column for the entering variable would be 0 on the row 0, and an identity, a unit vector corresponding to this guy, whoever that was, all right? So I have to make sure that in the next iteration, row 0 remains non-negative, which brings us to the ratio test of dual simplex, which is, I determined my leaving variable. Now the entering variable is an x for which the row 0 remains dual feasible. So first of all, it has to have a negative coefficient. Be careful. In simplex, the ones which had the negative coefficient was not working. This time, it has to have a negative coefficient, and it has to give me the smallest ratio of Rj over Yij in absolute value, because Yij is negative and Rj is small. Rj is positive. So you look at the negative entries and look the ratio of row 0 over the y. It was right-hand side over the y in the simplex. Now it's going to be row 0 over the y, but absolute value, because I want those y's to be negative. And you pick the one which has the smallest ratio. Again, smallest ratio wins. Then that variable will be my entering variable. I already determined my leaving variable. You do the simplex, as you always do, standard simplex iteration. Make ones and zeros, okay? Now, and that brings you to another iteration, hopefully with a less number of negative entries in right-hand side. Be careful, the unboundedness issue. Now, there is a row that wants to leave the bases, but everybody is greater or equal to 0. So there is no y here which is valid. There is no valid entry for my ratio test to determine my entering variable. That means it's already here. Dual can go all the way up because the dual was already feasible. So the dual actually can be unbounded. And I cannot, that means from weak duality theorem and the corollary too, the primal is infeasible. Because I don't have a feasible primal on my hand, but I have a feasible dual. I was just trying to justify its optimality. Well, I can't find a feasible primal that would give me a bound and values will be equal. That means the dual is unbounded and the primal is infeasible. Okay? Any questions on the machinery of the dual simplex algorithm? If not, I'll solve an example. Any questions? While I'll wait, I'll try to use this board again. I don't know why it's not working. Yeah, there is something in here that keeps on not writing out. All right. Any questions?
Hocam bir şey sorabilir miyim?
Yes, İrem. You want to say something?
Evet. Bunda da böyle degeneresi tarzı bir şey.
I can't hear you, İrem.
Burada da şu an duyabiliyor musunuz? Hocam. Sesim geliyor mu?
Is there any questions? All right. I go on then. Example. Suppose this is the problem. Okay, minimize z subject to these two conditions. Well, when you convert it to a max problem, then convert it to the standard form, right? Because I need, these are all non-negative, greater than or equal to constraint. I need two excess variables to convert it to standard form max problem. All right. Here's the table then. Yeah, what is the simplex? Minus x1 minus 2x2 subject to my constraints. If I write my table, this is how it looks like. Okay? As you see, if I leave it like this, okay, it looks row 0 is non-negative. So if I can find a basic solution without changing my row 0, then I could utilize dual simplex algorithm, because in the current form, it is okay to start with the dual simplex algorithm. So but I don't have an identity here, but I observe the fact that these guys can actually be utilized by just multiplying those constraints with -1, then I'll have this. All right, it's okay now because I'm going to use dual simplex. In the primal simplex, we weren't letting you to have a negative entry in the right time. You cannot have negative in here and negative in there. No, one of them should remain non-negative. In the primal simplex, we always have this guy non-negative. In the dual simplex, we want this guy to be non-negative. All right? So we observed that in the current situation, row 0 is non-negative, and there is something similar to identity matrix. So I decide to utilize dual simplex by multiplying everything there with -1, so that now this version is an okay version to use, okay, for dual simplex. Why? First of all, from here, I do have an identity, and basic variables row 0 coefficients are 0. So that's a valid simplex table for dual simplex. I have feasible dual and infeasible primal, which is okay in the dual simplex. So what do? I'll choose the most negative. Remember, before I go on, let's read this remark together. Normally, up until today, we were not letting you to multiply the excess variable constraints with -1 because that would leave us a negative entry in the right-hand side. And we were forcing the big M or two-phase to find the starting BFS. But now, this time, since we learned the other algorithm too, if the problem on hand can immediately start with the dual simplex algorithm, we're going to use that. All right? Okay, then, what does it say? This is the same table again, written here. Choose the most negative right-hand side, and that variable will be living. Most negative right-hand side is -6. So I have learned that E2 will be living. So the ratio test will go here. All right? Ratio test will go here. You look at the ones for which this is valid, and nothing else. Only X1 and X2 are valid because the algorithm says only the negative entries are valid to enter to the ratio test. You look row 0 divided by Yij. This one gives you a ratio of 1/2. This is absolute value of 1/-2 in the absolute form. This is 2/-1 in the absolute term. So this guy wins. This means X1 is entering and E2 is living. The iteration is the same. So this thingy should be 1. I need zeros in there. It's the same thing, right? When you do that, yes, here I have X1, and here's my table. This is the next iteration. I still have a negative entry in here, which is not feasible yet. But be careful, my row 0 is still non-negative because that's what I want. I have to remain a dual feasible. Okay, most negative is this guy, so E1 will leave. Who's going to enter? You need to check this guy and that guy. The ratios of those. If you look at the ratios, this will give you 1/3, so X3 is entering. All right? And this brings you to the next table, which is this. Now it's optimal. Primal feasible and dual feasible. So we're optimal. Any questions? We have just finished an example with the dual simplex algorithm. Any questions? Do you want me to reiterate any part? Yes, İrem. İrem, you're mute.
Hocam ben şey soracaktım. Yani biz niye bunu
But I can't
kullanalım?
hear you.
Herhalde.
Can anybody hear what İrem is saying? I can't hear you, but is it me or her?
I can hear her, hocam.
You guys are all hearing. I can't hear İrem. I can't hear you guys. What's happening? I don't know. I don't know. Then you have to write it in chat, İrem, what you're asking, because I can't hear you. I don't know why, but there is a problem with my hearing. And I can't correct it now. That means I'll have to do it in the break time. I opened it again. Somehow, what is RT? Is it? Okay. What is? Okay, I'll go one by one, but for my hearing ratio, of course I'll explain it again. I'll go one by one. Even though you guys heard, I didn't hear anything, so I'll fix that in the break time. But rengi seçtik, onu da bir daha anlatır mısınız? Anlatırım. Okay, the questions are: why is this useful? First question. It is, I guess, Irem's question. The answer to this is, for example, if we have such a situation in this example, normally when you write everything to the Simplex table, this is what you will be seeing. Okay, and in this case, we would be normally defining two artificial variables and either use BGAM or two-phase to start with a feasible solution, to find our feasible solution. Then we will go towards optimality. But if we observe that this table is actually feasible from dual simplex perspective, that means I can use dual simplex. The machinery of those two algorithms are very similar to each other. One works from the primal side, and the other works from the dual side. Other than that, it's always a simplex table that satisfies CS conditions with CBB inverse, the primal dual pair. Okay, so for certain problems, it will be easier to start with dual simplex if you observe. And I told you sensitivity analysis, some of our parameters would change, but I was at an optimal solution and all of a sudden something changed. Should I go back and solve everything from scratch again? Or should I put the change to my table and utilize what I can do? Well, for certain changes, dual simplex is what you're supposed to do. That's why we're learning this algorithm. So it's, again, repeat, utilizing the duality theory. Now, in addition to primal simplex, you have the dual simplex too. And in order to solve one of these problems, you can use any of these algorithms, all right? Both, because we know from strong duality theorem that their optimal solutions are the same, so it doesn't matter which one you're solving as long as you go on the correct algorithm. So you either have to maintain dual feasibility and use dual simplex, or you maintain primal feasibility. That means you're using primal simplex. So from Irem's perspective, sometimes the structure is easier for us to go with the dual simplex algorithm. Okay? Then let me go back to the other questions that's being şu tabloyu. Which table, Tolga? The one on here, or okay, let's go from here. The dual simplex, the ratio test. The ratio test was normally what we were doing in the primal simplex. We were taking the right-hand side, but we know which variable is going to enter, right? And we were looking at the ratio of the right-hand side to the column of the variable who wants to enter, right? That was in the primal simplex. Now we're in the dual domain, so I don't know who's going to enter. I only know who's going to leave, okay? Because from the dual's perspective, everybody's okay. Everybody seems all right. I'm in the feasible domain. I don't know which one is better. So, but I know which variable should go from the basis because the guy has a negative entry in the rows in the right-hand side. So when I use dual simplex, I know who should leave the basis first. Now, the living variable, well, this time then I have to look at the row of the living variable because this guy is going to go. Who will enter? I don't know yet. I'll determine. What I need to do is I have to remain dual feasible. I have to maintain the feasibility of the dual, right? Then the ratio test has to prove us that the dual remains feasible. That means I'll go, so because this is what I'm going to use. This row is what I'm going to use. So the ratio test is between rows this time. because it has to maintain dual feasibility. What is the dual feasibility? Rho 0 being non-negative. So this time the ratio test is within the rows, whereas it was within the columns, the primal problem, right? Primal simplex. So all you need to do is, once you do these, after the iterations, you have to have one in here and zeros in there. So you have to make sure that after your elementary row operations, your row 0 remains non-negative. Okay? And for that, all I need to do is check. Let me go back to the algorithm here. So you just look at the coefficient of the row, variable in that row, divided by its entry there. We are always dividing by coefficient of xj in primal simplex too. But this time, since I have to remain non-negativity in the row 0, you have to use the ones which are negative entries in the table. All right? Then once you make the selections like this, in the next iteration, which is what's happening in our case, so we choose it, that after the next iteration, you see our row 0 remains non-negative. If you have chosen x2, for example, as the entering variable, next iteration would be a mass. You will have a negative row 0 and a negative right-hand side, which means just gibberish. It has no meaning, anything. You can't use any of the algorithms. In order to use those algorithms, either primal simplex in the primal algorithm or dual feasibility in the dual simplex algorithm should be maintained. Okay? So be careful. In the primal simplex algorithm, we choose the entering variable first because our row 0 tells us putting which variable in improves our objective function. And then we see which variable hits the 0 first, which becomes our living variable. That's our primal simplex, good old simplex. The dual version, now we first determine the living variable because that's a negative there. I don't want it in my basis, right? So I want to kick that guy out of the basis. So now I'm thinking, which variable should I use to kick that guy out of the basis and maintain non-negative in my row 0? All the ratio test this time is to maintain row 0 non-negative. Okay? Let me go over these. So I explained ratio test. I explained entering variable. Why is this row 0 being non-negative? That means dual feasible. That goes to the proof of the strong delta theorem. Remember? Okay, let me try to. Well, my board is not working. I don't know why. So maybe I'll do it again in the next hour. But shall I? No, it doesn't work. Sorry, it doesn't work. It's in the proof of the strong delta theorem because row 0 is actually minus c. Hold on, this part is working. So row 0 is actually minus c plus cbb inverse a, right? If this is non-negative, this means minus c plus this guy is w. And that this means wa greater than or equal to c, which is my dual feasibility, right? So row 0 being non-negative is actually from dual's problem, meaning that my dual variable, dual vector w is feasible. Okay? Why is it unbounded? Because we already have a feasible solution in our hands. All right? Now, remember, we're using dual simplex. So the dual is already feasible. I'm trying to find a primal feasible. I don't have it yet. Dual is feasible, complementary slackness is satisfied. I'm trying to find primal feasible, but I can't. I can't kick the negative variable out of the basis. There is no entering variable which will kick this guy out of the basis. That means primal cannot become feasible. That means my primal is infeasible. Now, primal infeasible, remember what we were talking? Then the dual is either infeasible or unbounded because of the strong delta theorem. If primal is infeasible, dual cannot have an optimum solution. Dual will either be infeasible or unbounded. Well, dual cannot be infeasible because I already have a feasible solution on my hand. I'm using dual simplex. Yeah, the current W is feasible. So that only leaves me with one choice, which is dual is unbounded. All right? Do we observe CBB inverse under the row 0 coefficients of E1 and E2? Yeah. But normally, actually, I explained this, that the CBB inverse is underneath the rho zero coefficients of the starting BFS. And starting BFS requires my artificial variables. Okay. Right-hand side negative, that's why we have infeasible, exactly. In order to have unbounded, there is a living variable I want to kick out of the basis, meaning that its QI is negative. QI is negative. But all the Y's are not valid for my ratio test. Nobody enters the ratio test. I can't find any entering variable which will maintain my dual feasibility and kick this guy out of the basis. That's not possible. Then that means my dual is unbounded. If I'm using dual simplex. And yes, the ratio is absolute value because I'm using the ones for which rho zero, the underneath is a negative entry. So were we unconsciously maintaining dual feasibility in the primer? We're not maintaining dual feasibility in the primal simplex. We stop when we reach dual feasibility in the primal simplex. Yes. We didn't know that. You didn't know that back then, but now you learned it here. When we were using the primal simplex algorithm, we stopped when rho zero is non-negative. But we didn't know that. That was actually saying us that the dual became feasible. Now you're learning it because now you learned the theory also. So we used this up until in all the set 4 and 5, and we applied all those methodology. We entered and we left, and we see what happens when it's unbounded, blah, blah. And when we stop saying that, oh, rho zero is non-negative, we stop. Well, rho zero non-negative is actually dual feasibility. So when you stop because you reach dual feasibility. You're always primal feasible because your right-hand side is always non-negative in the simplex algorithm. And complementary slackness is always satisfied because I told you, I proved last time that the simplex table always satisfies complementary slackness conditions with CBB inverse and the basis, all right? And we stop when we reach the feasibility of the other problem. So in the primal simplex, we maintain primal feasibility and we stop when the dual becomes feasible. In the dual simplex, we maintain dual feasibility and we stop when primal becomes feasible. Hocam, if after our first step we have a non-negative rho, do we have to fix it by no? No, you shouldn't. If you do, be careful. If you do dual simplex, you have to maintain non-negative rho zero, always. If there is a negative entry in your rho zero and a negative entry in your right-hand side, you messed up. You made a mistake in your ratio test, go back. If you're using dual simplex, your rho zero always have to remain non-negative. I assume you meant negative dividends. Any other questions? Okay, let's give a break, and in the break time, I'll try to fix my environment. Let me stop recording.